Hello, and welcome back to the channel. Today we're diving into one of the most crucial aspects of modern software engineering: monitoring, observability, and reliability. Let's start with what I call the foundation of observability, the three pillars. Think of these as three different lenses through which we can examine our systems, each giving us a unique perspective. First, we have metrics. Imagine you're monitoring your own health, your heart rate, blood pressure, temperature. These are continuous measurements that tell you about your overall state. In systems, metrics work the same way. They're numerical values we collect over time, things like CPU usage, memory consumption, or how many requests per second our application is handling. The beauty of metrics is that they give us trends and patterns. We can see if our system is gradually getting slower over time, or if we're approaching capacity limits. Now, logs are quite different. Think of them as a detailed diary of everything that happens in your system. Every error message, every user login, every transaction, it's all recorded with a timestamp. While metrics tell us what is happening, logs tell us what specifically happened and when. When something goes wrong, logs are often our first detective tool. They're like forensic evidence that helps us reconstruct exactly what occurred. Finally, we have traces, and this is where things get really interesting in our modern microservices world. Imagine you're ordering food through a delivery app. Your single request, order pizza, actually triggers a cascade of operations across multiple services: authentication, inventory check, payment processing, delivery routing. A trace follows that single request as it bounces between all these services, showing us exactly where time is being spent and where bottlenecks might occur. Here's a key insight I want you to remember. These three pillars work together. Metrics might alert us that response times are high, logs might show us specific error messages, and traces help us pinpoint exactly which service in our chain is causing the slowdown. Now, let's talk about how we present all this information effectively. Dashboards are not just pretty pictures with colorful charts. They're mission-critical tools that can mean the difference between catching a problem early and having a major outage. Think about the dashboard in a car. What information does it show you? Speed, fuel level, engine temperature, the most critical information you need to operate safely. It doesn't show you the voltage of every individual component because that would be overwhelming and distracting. The same principle applies to operational dashboards. When designing dashboards, always start by asking, who is going to use this, and what decisions do they need to make? An operations team member who gets paged at 3 a.m. needs to quickly understand, is the system healthy? If not, what's wrong and how urgent is it? They don't need to see every possible metric. They need the right metrics presented clearly. Here's a design principle I always emphasize. Your dashboard should tell a story. Start with the big picture, overall system health, then allow users to drill down into details. It's like a newspaper. Headlines first, then the full story if you need it. Use visual hierarchy to guide the eye to the most important information first. And here's something many engineers get wrong. Color matters tremendously. Green should always mean good, red should always mean urgent attention needed, and yellow should mean caution. Be consistent across all your dashboards. I've seen systems where different teams used different color schemes, and it caused confusion during critical incidents. Alerting is perhaps one of the most challenging aspects of observability to get right. The goal is simple: notify the right people when something needs attention. But the execution? That's where many organizations struggle. Let me start with threshold-based alerting, which is the traditional approach. It's like setting an alarm clock. You define a specific value, and when a metric crosses that line, an alert fires. For example, alert me if CPU usage exceeds 80% for more than 5 minutes. This approach is straightforward and predictable, which is why it's still widely used. But here's the problem with pure threshold-based alerting. Systems are dynamic. What's normal for your system during peak hours might be very different from what's normal at 3 a.m. A 50% increase in traffic might be catastrophic at midnight, or it might be completely normal during a product launch. This is where anomaly detection becomes powerful. Instead of static thresholds, anomaly detection learns what normal looks like for your system and alerts when behavior deviates significantly from that norm. It's like having a friend who knows you really well. They'll notice when you're acting differently, even if you can't articulate exactly what's changed. But here's the key insight. You don't have to choose one or the other. The most effective alerting strategies combine both approaches. Use thresholds for critical, well-understood boundaries like database connection pool is 100% utilized, and use anomaly detection for more subtle, complex patterns. Remember, the worst thing that can happen with alerting is alert fatigue. If your team starts ignoring alerts because there are too many false positives, you've defeated the entire purpose. It's better to have fewer, more accurate alerts than to overwhelm your team. Now we're getting into what I consider the heart of reliability engineering. These three concepts, SLIs, SLOs, and SLAs, form the foundation of how we think about and measure service quality. Let's start with SLIs, or Service Level Indicators. Think of these as the vital signs of your service from the user's perspective. Just as a doctor measures your pulse, blood pressure, and temperature to assess your health, SLIs measure aspects of your service that directly impact user experience. The key word here is user's perspective. We don't care that your CPU is at 60% utilization if users are getting fast, reliable responses. Common SLIs include latency. How long does it take to respond to a request? Availability. What percentage of requests succeed? And error rate. What percentage of requests fail? These should be measurements that correlate directly with user happiness. Now, SLOs, or service level objectives, are where we set our targets. An SLO is essentially a goal. We want 99% of our requests to have latency under 300 milliseconds. Notice how specific this is. It's not just we want to be fast. It's a measurable, time-bound commitment. Here's something crucial to understand. SLOs are not about perfection. They're about finding the right balance between reliability and other concerns like development velocity and cost. Setting an SLO of 99.99% availability sounds great, but it might require so much additional infrastructure and operational overhead that it slows down your ability to deliver new features to users. Finally, SLAs, or service level agreements, are the legal contracts built on top of your SLOs. These typically include consequences for not meeting your objectives. But here's an important point. SLAs are primarily external-facing, usually part of contracts with customers. Internally, you should focus on SLOs to drive your engineering decisions. Think of it this way. SLIs tell you what to measure, SLOs tell you what good looks like, and SLAs tell you what happens if you don't achieve good. This is a distinction that I see even experienced engineers confuse. So let's take some time to really understand the difference between high availability and reliability. High availability is about uptime, keeping your lights on. It's measured in those famous nines we always hear about. 99.9% availability means your system is down for about 8.7 hours per year. 99.99% availability means about 52 minutes of downtime per year. High availability is achieved through techniques like redundancy, failover systems, and load balancing. But here's the critical insight. A highly available system is not necessarily a reliable system. Let me give you an example. Imagine a banking system that's available 99.99% of the time. It's almost never down. But when it is running, it occasionally processes transactions incorrectly, maybe debiting the wrong account or processing a payment twice. This system has high availability but low reliability. Reliability is broader. It encompasses not just availability, but also correctness, consistency, and predictable performance. A reliable system not only stays up, but when it's up, it behaves correctly and consistently. It's the difference between a system that's just running and a system that's working properly. Think about this in terms of a car analogy. A car that starts every time you turn the key has high availability. But a reliable car not only starts consistently, it also gets you to your destination safely, maintains consistent performance, and doesn't break down in unexpected ways. In practice, reliability is the more important concept because it encompasses the user experience holistically. Your users don't just want your system to be available, they want it to work correctly when they use it. Let's talk about health checks, which I like to think of as your system's way of communicating with its orchestrator. In modern containerized environments like Kubernetes, these probes are absolutely essential for maintaining system health. Imagine you're a manager overseeing a team of workers. You need to know two things. First, is each worker alive and functioning? Second, is each worker ready to take on new tasks? This is exactly what liveness and readiness probes do for your applications. A liveness probe answers the question, is this application instance still alive? It's checking for scenarios like deadlocks, infinite loops, or processes that have become completely unresponsive. If a liveness probe fails, the orchestrator takes drastic action. It kills the instance and starts a new one. It's like a manager saying, this worker seems to be completely stuck, so I'm going to replace them with a fresh worker. A readiness probe, on the other hand, answers, is this application instance ready to handle traffic? This is more nuanced. An application might be alive but not ready. Perhaps it's still initializing, loading configuration, or connecting to databases. During deployments, new instances need time to warm up before they can handle production traffic. Here's a real-world scenario to illustrate the difference. Imagine you're deploying a new version of your application. The new instances start up, and they're alive. Liveness probe passes, but they're still connecting to the database and loading cache data. During this initialization period, the readiness probe fails, so the load balancer doesn't send traffic to these instances yet. Once initialization completes, the readiness probe starts passing, and traffic begins flowing to the new instances. The beauty of this system is automation. Without these probes, human operators would need to manually monitor application health and make decisions about routing traffic. With probes, the system becomes self-healing and self-managing. Finally, let's discuss what happens when things go wrong, because they will go wrong. The question isn't whether you'll have incidents, but how you'll respond to them and what you'll learn from them. Incident management is your playbook for crisis response. When a system fails, every minute counts. You need clear processes for detection, assessment, response, and communication. But here's what I want to emphasize. The goal during an incident is not to find fault or assign blame. The goal is to restore service as quickly as possible while minimizing impact on users. This brings us to one of the most important cultural concepts in modern engineering, blameless postmortems. Now, when I say blameless, I don't mean accountability-free. I mean we focus on understanding the system failures and process gaps that allowed the incident to occur, rather than punishing individuals. Here's why blameless postmortems are so powerful. When people feel safe to discuss what went wrong without fear of punishment, they share more complete and honest information. This leads to better learning and more effective prevention strategies. A good postmortem asks questions like, what sequence of events led to this incident? What warning signs did we miss? What tools or processes could have helped us detect or respond faster? What changes can we make to prevent similar incidents? The goal is continuous improvement. Every incident is an opportunity to make your systems more robust and your processes more effective. Organizations that do this well often find that their systems become more reliable over time, even as they grow in complexity. Remember, failure is not the opposite of success. It's a stepping stone to success. The most reliable systems in the world weren't built by teams that never made mistakes. They were built by teams that learned effectively from their mistakes. This concludes our overview of monitoring, observability, and reliability. These concepts will be fundamental to your work as engineers, regardless of which specific technologies you use. The principles we've discussed today, the 3 pillars of observability, effective alerting, SLOs, reliability thinking, health checks, and learning from incidents, these will serve you throughout your careers. Before you go, I'd love to hear from you in the comments. If you found this video helpful, do give it a like, share it with your friends, and of course don't forget to subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.